Our next speaker is Andrew Margenot. Dr. Margenot addresses the literal foundation of all cropping systems, soils. He advances how we monitor and use soils as natural capital with an emphasis on nutrient and organic matter management. His team works to support efficient use of N&P here in Illinois and to support agriculture in meeting the Illinois NLRS goals. Andrew Margenot. Doctor?
All right, well, thanks for having me. So my name's Andrew. I'm a soil scientist by training. As you're gonna see, I work with non-soil scientists like hydrologists, and I think that's important because, as I hope to convince you of in the coming 45 minutes, a lot of our understanding of non-point sources has to engage beyond soils to consider the aquatic sphere of our landscape. So you really have integrated hydrological terrestrial systems. So it's a fancy way of saying look at the stream and look at the soil together. So what I want to present today is the result of one of our NREC projects that has been supported as of 2021. This is a project that is looking at both agronomic and water quality outcomes of what we call legacy phosphorus. That term you'll hear a lot about. I'll give you a more firm definition, but a working definition for now is it is phosphorus that was put down either as fertilizer or as erosion, and it's still there. So the word legacy here does connote a historical time component. And the reason why we care about this, if you walk away with one thing from this, is that there might be lags between when we implement a BMP, even in point sources, but really especially in non-point sources, a lag between when we do a BMP and when we see that translate to a detectable improvement in water quality, here defined as measurable total phosphorus loads. Okay, so of course it takes a village to do research like this, so here are some of the members of my team that are focused on the phosphorus angle. What you're about to hear is largely from their efforts. So our research team, our goal is utmost to support the profitability and sustainability of agriculture in our state. And we do this by applying biogeochemistry, which is a fancy way of just saying, how do nutrient elements like phosphorus, nitrogen, carbon, how do they flow through land and air and water? So we're in the business of quantifying how much and how fast. And when it comes to phosphorus and its lag times, I think this lens is fairly fruitful. Now today, I want to talk about really three things. We want to look overall in this coming 40 minutes about what are maybe some blind spots that we have with respect to our phosphorus balance account. So when we're talking about non-point sources, are we missing any part of the picture? And this again goes to not just the how much and how fast, but also from where. And I'm trying to convince you today that the from where part, we may have missed something that could be potentially kind of big. To do this, we're going to talk about three things. So the first is going to be subsoil P supply power. This is a agronomic take on legacy phosphorus. So legacy P is not solely about decreasing phosphorus exports in a timely manner. It also relates to how we manage fertilizer, and specifically the critical soil test value. So 40 pounds of Bray P per acre, this is itself impacted by legacy phosphorus. So that's the first chapter. The second chapter will be talking about, well, let's look at soil phosphorus from past applications that has accumulated. That's legacy soil phosphorus. And then we'll talk about how we can get a different kind of legacy P as sediments, as we've just heard. And these sediments can encumber a very long lag time. And they get into the streams in large part by streambank erosion. This is a blind spot that I want to bring to our attention in the state. It might be worth thinking about as a target of nutrient loss reduction efforts. So, chapter 1. Let's talk about subsoil P supply power. This is not a new concept. It's my predecessor, Dr. Cyril Hopkins, shown here in 1905. He was really the first soil scientist on our campus that did things like mapping the state's soils. He began that effort in 1899, and as you'll see, we are still reaping the benefits of that wise investment. So what Dr. Hopkins was doing in 1900s, 1890s was mapping our soils in the state. This is before we even had ways of classifying soils, so they were called things like brown forest soils. And what I want to point out is that they were in the business of quantifying how much, quote, plant food is how they termed it. So what were the stocks, basically? How many pounds per acre in the top 6, 12, 40 inches of N, P, and K? So not a new concept, and it makes sense that back then they were trying to understand our soils from the perspective of how much of P and K are stocked up. So that concept then eventually evolved, to the best of our knowledge, into what we find in Chapter 8 of the Illinois Agronomy Handbook. That's what we see right here. And so we see a figure and then, two figures. The one on the left is the map of what we term subsoil P supply power. It's a really clunky term. All it means is that if you go beyond the top 7 inches from which we typically pull cores for soil testing, there's obviously more soil, and in our soils, that depth can go quite deep. You can go sometimes 6, 7 foot. And importantly, there are nutrients that are plant available that are stockpiled in the subsoil. And we can credit some of our crop uptake to that subsoil P. Think of corn roots can get down to 6 foot. Now, this matters because the nutrient recommendations on the critical value in the handbook, which will inform whether you make an application or not, these are predicated on what region do you find yourself. So if you look on the your right-hand side, on that figure, the soil test response curve, what you're seeing is a classical agronomic tenant. This is bread and butter. It shows on the x-axis the pounds per acre of Bray P units, and you see that yields on the y-axis level off. This is a very qualitative concept. These aren't really firm numbers. But the idea is that you don't make an application because it's not economic once you surpass the critical value. But note that the critical value is coded by those 3 shades of green, from dark green for the high subsoil P supply power, a lower critical value, to a higher value if you're in the lower supplying region. So all this means is that if you find yourself in western Illinois in a hotspot of high subsoil P, you don't have to put on as much for the same target yield. So there's a 25% difference in how you might interpret the same value on your soil test, depending on where you find yourself on this map. Now, the map obviously is very coarse. It's a good start. I want to talk about where this came from. This will set the stage for Legacy Phosphorus, and also there's some important updates that we're trying to make to this map. So first, this subsoil supply concept is the product of 3 things. First is how thick is the loess, second, how old is the loess, and third is drainage. So beginning with the first 2, the thickness and the age of the loess. Loess is simply the fine talcum powder consistency material that was blown in post-glaciation. So we're talking, well, 10,000 years ago, there was a block of ice where we're standing, or it had just melted, and then winds just blew and blew and blew, and they deposited a pillow of this fine silty material. Now, that pillow can be as thick as up to 20 feet in the west part of the state, more typically 6 to 8 feet, and as you angle out towards the east side, it gets lower. So there's a mantle, a blanket, if you will, and our state is one of the only states in the union that has almost full coverage of all of our lands in this loess. Iowa has a good chunk, but not all of it. So that's the one thing, that's one component, and it makes sense. You have more loess, deeper loess, there's more subsoil P there for the crops to scavenge. The second would be the age, and basically this is the right-hand graph. These are from the 50s and 60s, and what it shows is that the darker north-central lobe where we find ourselves, it's younger loess, more recently blown in. Younger loess has more of its P left. The older loess that you find in west and south Illinois, it's been there for longer, it's begun to leach out some of the P over geological timescales. So if you got younger and deeper loess, you're in a good place. Now, those maps are older, but if you look at the more recent maps by the State Geo Survey, you find overall good correspondence. You get thicker loess in the west overall and shallower on the eastern half. But if we go back to the map on the left-hand side, there's obviously some disparities, right? And what we're trying to do with this NREC project is trying to update that to be field scale informative, not kind of guessing where you lie on that map. So the third component that is in this equation is drainage. And this is perhaps one of the biggest things that we have to update the handbook for on this concept. The concept of drainage is that if you have a high water table, as we heard from the very first talk, that's going to impact things. In the case of roots, if you have a high water table, the roots can't get down there. So with drainage, or with better drained soils, let's say, you have more accessibility to the subsoil P. The problem is that these maps were based on the natural drainage classes, and that's what you're seeing on the right-hand side. More blue is less well drained, poorly drained actually. We live in a semi-marshland. Because we've been doing tile drainage since the 1890s or even before then, this concept may not apply that well. So one question is, given that even by the 1940s, like in this map, we were well aware that we were altering the hydrology, maybe this concept of subsoil P supply power, it may not be that valid. So one way to do this is if we have estimates of drainage areas, we could update the map. This is why we might find regions that have fairly thick loess. They were originally classified as low supply power because they weren't being counted as being drained. So I'm trying to lay out here the considerations for a grain of salt when it comes to this map, and thus how you interpret your soil test values. Okay, so one question too is where those values come from. High, medium, and low is nice, but they're categorical. So we'd like to make this a numerical, quantitative scale. And second, we're trying to tie this to soil types. And as we'll see in chapter 2 of this, we do have a way to do this. The idea is that we have soil types mapped across the state. That's existing. If we can integrate into that data layer of a map, then we can provide at the field scale, like shown here, specific recommendations on what field site subsoil P supply might be. So that's the first part of our work, and I'll tell you in a second how we're going to achieve the updates to that map. But first, we should talk about Legacy P in soils. These are two sides of the same coin. So Legacy P in soils, again, is phosphorus that was put down as a net input from a past application. This could have been 2 years ago or 200 years ago. And it is thought to contribute in part to our non-point phosphorus losses. So to set this up, I want us to consider what I think of as a paradox in terms of we are the biggest contributor of phosphorus to the Mississippi, but we're also, I think, well, the data suggests we are one of the most efficient in terms of our fertilizer use. And that seems like a paradox. How can we be the most efficient in the union and yet the biggest loser of P? So this is a map from USDA data. It is an estimate of P use efficiency, PUE. It's simply a calculation of how much grain phosphorus, or rather, how much phosphorus do you take off with grain, and how much P is being put into the system. These are coarse, county-wide estimates with all the caveats there. But you can see here that Illinois, especially central and north, and the south as well, we're doing pretty good, if not the best in the country. So we're looking at 60% plus in the south, and we're upwards of 80% P use efficiency in the central north region. Compare that to some southern or southeast states, we're doing a lot better. Any guesses on what the global P use efficiency is? Given that we're at 80% where we're standing right now. 30? Excuse me? 35, 30, okay. It's about 16% globally. So we're doing pretty good in the US, especially in our state. But again, we're also a high loser from non-point agricultural sources, and that distinction I think is important. So there's no paradoxes in anything, there's just really bad explanations. And I think the explanation here is the magnitudes we need to reconcile that these are simply just different. What constitutes a big loss, environmentally speaking, for water quality is not the same as an agronomically appreciable loss. So to do some math to walk you through this is also USDA data. Here, the darker shading means more phosphorus losses. And this is accounting for point and non-point. It's all together. So if we pick a dark color, let's say 200 kilos per kilometer, I can't really make sense of that. So to put that into units of pounds per acre, we're looking at about 1.8 pounds of P per acre is 200 kgs of phosphorus per square kilometer. So that's, imagine yourself in those black hot spots. So environmentally speaking, to be a hot spot of loss in the Mississippi Basin, it's 1.8 pounds of P per acre. Not a whole lot, especially if you consider that application of 200 pounds of DAP per acre is putting down about 40 or 41 pounds of P per acre. This is P, not P205. So we're talking something like a small percent, the total application being lost is proportionally speaking not so huge agronomically, but environmentally that's enough to register as a US-wide hotspot. And to put it differently, flip it, if we're 95% efficient with our P applications, the 5% that we might be losing is still enough to drive large impacts on water quality. And we, I think, should discuss what is an acceptable use efficiency for lots of nutrients. Global PUE is 16%. we're at 80% in Illinois. So even if you're at 95%, you're still going to have some leakage. So that's for context. Now, one question might be, well, how much are we actually losing from fertilizer applications in Illinois? And broadly speaking, we don't have a really firm answer from fertilizer. We can get at the agricultural non-point source, but that might include things like erosion. And in fact, it seems like erosion, by and large, is the main driver overall in any cropping system. The hillier that you get, more hills, more slope, the greater the proportion, the slice of the pie of phosphorus from an ag source that's erosion. This means we have a soil conservation challenge, not an over-application challenge. Okay, now a second question might be, okay, well, of the P that we lose from fertilizer, how much is from this year's application? So if you register a DRP load in a river, was that from this fertilizer's or this year's input, or was that maybe from 100 years ago? And here's a good example. This is courtesy of Lowell Gentry and Dan Schaefer at the Douglas County site, where they did some nice detective work to give an example of this. So in circle here is a homestead image from 1940. And if we zoom in on that, this homestead is overlain on the right-hand side with tiles that Gentry and Schaefer are monitoring for DRP losses. And what you see in the little red circles as they get darker red, that's a higher Bray value. So we're getting up to, in ppm, about 130 pounds ppm. So we're talking like plus 250 pounds per acre of Bray P. Remember, 40 is the critical value. So we got plenty of P there. And the hot spots are right where the pens or the holding area was for the livestock. So this is 1940. The P is still there from 2000. I believe 19 when they had sampled this. And furthermore, we found that, well, they found, excuse me, that as you increase the Bray P test value at these very high rates, you see an increase in DRP export through the tile. So we might be leaking P, slow release, not in the good sense, through our tiles or as surface runoff from past fertilizer, or in this case, manure that was put down 60, 70 years ago. So then a more full definition of this concept of legacy phosphorus. Again, it's unused P inputs. It could be fertilizer or manure. And the important thing is that it doesn't matter if it was 2 years ago or 200 years ago, it might still be liable for crop use, which is a great thing, but also for losses, which is not a great thing, especially if we're trying to attribute in-year losses to a in-year practice like application. There's a disconnect, a decoupling of those, temporally speaking. So this, to put it mathematically or from an agronomic standpoint, you have a positive balance, right? So if you add up your inputs and your outputs, positive balance, like your checkbook, good thing, means that you have net accumulation. So if we have a negative balance, or that means that we're mining. So a zero balance is the ideal, right? You have a maintenance application. Now, again, because phosphorus, unlike nitrogen, which is very fleeting and does not want to stick around, it's got commitment issues, phosphorus will be there forever. And so because of this, we can count on the P from a past application sticking around, especially in our clay-rich soil types. So to integrate these two concepts of balances and PUE and legacy P, I know I'm throwing these terms around. Here's a simple diagram to just to illustrate it. We've got in the green phosphorus balance. So as we go from positive of 100, we get to 0. 0 is the ideal for a maintenance rate. We can also get a negative balance. We're mining. And phosphorus use efficiency can also go above 100%. So if you think about that, it means that you're exporting more with the crop harvest than what you put on, but that's because you're mining the soil. So you can have a over 100% phosphorus use efficiency. So these are inverse. More positive balance means a lower P use efficiency for that year's scale at least, and it also will entail net accumulation, so that's going to be more legacy P being built up. So now the question is, how do we monitor this? And that's what we're trying to do in this NREC project. Well, you can directly measure the total phosphorus stocks, but importantly, not the original native phosphorus, but what we have accrued. There's no isotopes of phosphorus, unlike nitrogen, that helps us with this, or for carbon. So we really have to look at a before and after. Unless you have a time machine, you can't quite do this, right? We kind of have a time machine that I'll share with you in just a second. So the main approach is indirect assessments by, say, soil test P trends. The problem, though, is that soil test P trends, test P is about 15% at most of the total legacy phosphorus. So it's a qualitative marker, but it's not going to be a quantitative way to that was a bit redundant. It's not the way to quantify your magnitude. Okay, so I'm going to walk you through two approaches that we're using in this NREC project, and then I'll show you the direct quantification. So indirect ways of getting at an estimate are going to be your soil test values and the balances. So there's pluses and minuses of these. Soil tests, we all know these as Bray or as Melic. It's an extractant, and it's going to get you a small amount of the total phosphorus. And the benefits is that they do track more or less as a proxy with total phosphorus, so you can get a sense of legacy P buildup. It's also good because these are widespread in use. The issue is that they also can be used to gauge the risk of runoff as dissolved reactive phosphorus. The problem, though, is that they're not total phosphorus measurements. So for balances, what we're talking about is you would sum up the inputs and the outputs, and the difference is the balance. A positive balance is a legacy P credit in some sense. So benefits for these is that they're well established. These are basic tools in agronomy, biogeochemistry. And the problem is that they get tricky to do as you get fine scale. As you zoom in space and time, so short time periods, small areas like a field, they're very difficult to calculate with confidence. The uncertainty increases. And this is because look at what you need as the input and output data, especially over a long time. So imagine one field over 50 years, it's hard to get all that information. Okay, so let's start with some soil test trends. And this is going to be a line of evidence that suggests that in Illinois, the results seem to suggest that we're not over-applying phosphorus in the last few decades, but historically we may have encumbered a pretty large accumulation that is still leaking phosphorus today. So in terms of the evidence for recent over-application, we see the opposite. We see evidence from soil test P trends shown here that we're actually drawing down. So economically, this is a good thing. It's a good stewardship practice. It's saving people money. What you're seeing here is in the union and then in the state, left and right-hand side, respectively, what the Bray test P values look like. And the y-axis is simply the percent of soils in the U.S. or in Illinois that test in that range. So again, the critical value is about, in this case, it's in ppm, 15 to 20 ppm. And I've shown with the red line, if you're above that higher value of about 30 ppm, so 60 pounds per acre, you're probably good on not applying more. You can afford to draw down a bit. So what we see is that if we subtract the 2 time points of these data, which are anonymously collected by IPNI in 2001 and 2014, the difference, so the 13-year difference between those, 14-year difference, will look like this. So if you're above the x-axis, you're increasing the proportion of soils in the U.S. or in our state that are in that category, in those different categories of Bray test. If you're below the x-axis, you've decreased the soils that are testing. And what we see is a good thing. We see soils that are well above any economic yield response. There's less of those soils in Illinois during this 2001 to 2015 period. Economic sense, stewardship makes a lot of sense as well. And we've actually beaten out the US average, so we're doing a better job at drawdown. Almost too much. We have some increases in the sub 10 ppm, so we could risk a yield drag in some soils if we're at 10 ppm Bray. But this is not showing, this is exactly opposite if we were over-applying phosphorus at a state scale during this 14-year time interval. So that's line of evidence number one, that we've not been incurring net accumulation in the teens of this last decade. Second are agronomic balances, and these are going to be shown for county and then for statewide. I'm going to begin with county across the state. So 2 sources, we've got federal data, USDA on the left, and we've got Illinois Department of Ag on the right-hand side from different dates. To walk you through these, on the left-hand side, this is, again, county level. We're looking at the inputs and the outputs. And what we're finding here is that things get more orange over time. And more orange, less blue means that there's more mining of phosphorus. Now, some observations, it's obviously quite stratified by the county, and it can fluctuate by year. Because this is looking at fertilizer sales in each county, this makes sense. It's noisy data. So looking at multiple decades gives us a better trend. But the theme is that we're not overall having dark, dark blue large positive balances across every county for the last, in the more recent decades. On the right-hand side, we've got a different approach by Dr. Sagdapur and his group. They're part of this grant. And what we're seeing here is this is also the county in dark green, which show a more positive balance. A lighter yellow is going to be a negative balance. And basically, we can vary from a moderately large positive balance, tens of pounds per acre, to a negative balance of about 11 pounds per acre. So this is, again, very coarse, but it gives you an appreciation, perhaps, for how dynamic and how variable these balances are year to year. And that's one of the challenges with this technique. So if we scale out over larger spaces and over larger time scales, we have more certainty in these estimates. So again, the goal here is to see how we've been over-applying in recent decades. This is a figure from a paper by Mark David and Lowell Gentry, published in 2000, and they looked at since 1945, so multiple decades, what are the trends in phosphorus inputs, the use of manure, sewage, and importantly, the riverine export. That's what we're trying to decrease as part of the NLRS. And so you see that the manure application rates are going down. Manure is not a net input at a state scale. We're just recycling the P from the system. Hay is already having P from the soil. The net inputs would be things like this. They're being brought into the state. Could be manure out of state. It's largely going to be fertilizers, MAP, and DAP, and even some rock phosphate in the 1940s and 50s. And so I've added, for context, what we've calculated to play out the x-axis a few more decades. And what you see here, some observations, if I've recolor-coded this to make it more digestible, the area beneath the curve of net inputs is basically the amount of legacy P that we have at the state scale, using this paper's data. And their calculation was about, it was in megagrams, so that's going to be 4.9 billion pounds of phosphorus were applied, largely from about 1960s to about 1980s and 1990s. So note that by 1990, we're in the red. We're actually mining soils. This is on a balance perspective, but we had built up quite a bit in green in the previous decades. So this is exactly what the magnitude could look like in our state. 4.9 billion pounds sounds like a lot. We tend to talk about tens of millions of pounds in the strategy. So to give some context to this, our soils hold a lot of phosphorus. So if we make some assumptions here about, yeah, that's about 203 pounds of P per acre, that seems like a lot, but our soils are holding about 20 times more than that. And so if you do the math on 3-foot depth and the bulk density, the P content that we've been developing from this project, the 4.9 billion pounds that we incurred, that we still have in the bank account in green, is only 5%, we estimate, of the total phosphorus stock that was already naturally there. So it seems like a lot, but again, context matters. It's a small amount. Still, there can be big impacts, yet again, on water quality because of the disparity in magnitudes. All right. So I talked about a couple ways to triangulate. We're indirectly trying to hone in on what the legacy P magnitude is. You've seen some examples. There's a more direct way that we can cut to the center of this. And we don't have a time machine, but we have the next best thing, which is an archive on this campus of soils that were taken as far back as 1861. The majority of them are around 1900 to present day. And so because we have this archive of soils, and a few of you have seen this, it's row upon row of shelved and organized jars with soils, and we know where the soils were taken, we can analyze soils and know in this county in this year, before P inputs were being used on broad scale, we can calculate the actual native soil P amount, which, by the way, gives us the subsoil P supply map that I just talked about. So we achieve the agronomic update there. And then if we resample the same location today, we can find out over X years since they last sampled it, as far back as 1861, how much net phosphorus has accumulated. So this is really rare. So to show you why this is, I think, pretty cool and gives us a unique opportunity to test legacy P, to quantify it, our archive is one of the oldest in the world. This is some work. I work with USDA scientists on this topic of historical soils, and we found that our archive of pedons, these are soil pedons to 3-foot depth used to map the states, Dr. Hopkins, 1899, our pedon collection alone is at least a century and change. So you're seeing here a global meta-analysis of all of the archives in the world. And so already we're in the top 5% of age. If you look at the Maraplot soils that we also have here, beginning that start in a little bit before then, we get easily now to pass the 100-year mark, 120 years of Maraplot soils. And then if you think about our oldest sample that we have, 1861, we tie with Rothamsted. And Rothamsted, in case you don't know, is the oldest continuous experiment in the world in the UK. The second oldest is the Maraplots. And so we basically are a global leader in being able to test questions with this archive on how have we altered phosphorus stocks. So here's an example of the oldest sample. Thought you might appreciate it. This is 1861. I've tried to transcribe the, I think, probably quill ink writing on the label there. Amazing that it's still there and not decomposed. And you can see it's, quote, virgin prairie, original prairie from 1861 in Perry County. So I think that's quite neat. Civil War was just starting at that time. So these soils are PED-on. This I want to stress because we need to have PED-on data to quantify legacy phosphorus in things like streambank erosion contributions. So PED-ons just mean that we look at a soil profile. Here we have our state soil, the Drummer series, and you can conceptualize, of course, this is what you have in the textbook and what the exam looks like, right? The simplified version versus the reality. We have different layers. We call them horizons. They're different. The point is that they're depth explicit. And so that's important because you might have legacy P in the topsoil, and subsoil P supply power is going to be in the bottom part. So we can use this archive for the dual purposes of updating that map of subsoil P supply power and quantifying directly, and I think we're the only state that can do this, the legacy P magnitude. So this is more about the archive. Map is the coverage we have of the state. So almost every county has a couple observations. And the chart on the right is showing us what we have as the PED-on collection of the high quality observations. We know exactly where they took this as far back as the early 1900s. And then in red, we have what the federal scientists have. So we're trying to repatriate these soils back to our home state. We're going to be up there next month to bring back a few thousand samples to extend the PED-on collection back to present day. So that way we have 100-year of full coverage across the state. This gives us what's called a chrono sequence. So chronos, chronology, Greek for time. If we sample a site that was sampled in 1920, we sample it this summer, that's 102 years since they last sampled. And so if we sample more recently sampled to less recently sampled, we have a gradient of age. And now we can test in a geographically explicit fashion at the county level what have been the changes in phosphorus. The delta, the change in P since the time of sampling to today, that is legacy phosphorus. We can also test if there's been mining of phosphorus in some parts of the state. Okay, so this gets into how do we manage legacy phosphorus. And for this, I'm gonna just quickly say a few words about drawdown. Drawdown is an agronomic tenant. If you have a high soil test value, you don't need to apply. There's no economic probability of a crop response. And just for what it's worth, they were thinking about this back in the 1900s. This is, again, 1905, Dr. Hopkins, talking about how many crops worth of P are stored up. Now, this is obviously thinking about the native phosphorus, and it's not suggesting that we should mine our soils. It doesn't work that way. You have a yield drag far well before you would draw down 50%. But the idea here is we can just cut back on rates, potentially. The key is to use soil tests. So I'm gonna give you two examples of drawdown. One is a third of a century, one is a century and a half. This is from Monmouth, where we've got drawdown. The net phosphorus that we export is what you see beneath the x-axis. Above the x-axis is the application. So we applied phosphorus once in 37 years because the soil test p-value, shown here as MELIC, never got below the critical threshold trigger of 20 ppm. See how it oscillates? It's kind of noisy. But it hit down to 20 ppm or beneath that in 2010. We hit it with 200 pounds of DAP. That's what you see as a small sliver above the x-axis. Otherwise, we kept taking off across 4 different systems, corn and soybean for 37 years. So that's about 1 metric ton per hectare. So roughly about 2,000 pounds per acre were mined from these systems. But that magnitude, which is shown in the little red box on the bottom graph on the right-hand side, that is still only at most a third or as low as 1/5 of what was already in the stockpile. This is a good example of how, because of past manure application, prior to 1980, there was enough phosphorus to take off 36 crops without having to apply phosphorus. So that's a good thing in terms of saving money for the farmer and also decreasing the DRP loss risk. Second case study is our very own Maro plots here on campus. These are actual photos of us, well, in present day sampling with, I think, more effective hat gear than what they had back then. And so what you're looking at here is 145 years of a phosphorus balance. This is the oldest, to our knowledge, in the world. And we begin in 1876 through present day. We got two systems, one in blue, which is fertilized, one is in orange, not fertilized. So corn on corn, 145 years. We pulled off the harvest 145th this past November, and we see that we're mining soil in orange. That makes sense. Look at the blue line. We've got 4 different phases of phosphorus inputs. So first phase, there were no phosphorus inputs. People didn't have phosphorus as a fertilizer, even prior to 1890. And then we see phase 2, where we're using rock phosphate. So the rock phosphate usage then, this led to most of the legacy P that we see today. So in phase 2, we induced a large positive balance. We drew down a little bit in phase 3. At phase 4, we increased a little bit with the introduction of DAP because it was being applied not on a maintenance rate, but on a threshold basis. The point here is that we've incurred most of our legacy phosphorus, the positive balance, at the Maro plots, in only about 15% of the total duration of the 145 years. So a lot can happen in a short amount of time. Okay, so then the final chapter here, I think I've got 10 minutes. Okay, perfect, is the other kind of legacy phosphorus, which is the legacy phosphorus that is in our stream channels. And a couple of the talks before this have hinted at this or even talked about it. So this is phosphorus in the stream channel. How it gets there is really through 2 ways: overland erosion and also stream bank erosion. We'll show you some examples that we've done to show you how variable, but also how important this is to getting it right on the attribution of P losses within non-point source. In short, if we don't count stream bank erosion, we may be unfairly counting it as an agricultural loss when it's actually the stream bank non-point loss. So stream bank erosion, as the name implies, you're slowing off the bank, and these are soils, very much so. This is the literal interface of terrestrial to aquatic. And here's some really bad examples of what it looks like, and also examples of how you might manage it with stream bank stabilization on the right-hand side. So because there's a lot of mass, even if you have 300 part per million, that adds up over the thousands of miles of streams, and we're talking even small creeks across the state. Here's an example of how much this can vary. We did some sampling with Jennifer Jones in the Polecat Creek. This is a tributary of the Embera River. And we just wanted to assess how variable is stream bank phosphorus content, and thus with erosional loss, how much could that be? So these stream banks are shown here as a few examples. These stream banks varied from being very short off of the stream bed, a couple feet, as you can see, a little bit longer, and some were really deep. So this is a loess bluff. That's actually the loess parent material that you're seeing, about 30 foot deep of it. And that has been cut. So we've injected all that phosphorus through the sediment into this tributary of the Embera River. So our question was just, what's the magnitude that we're looking at in Illinois systems? And here are example profiles. We're soil scientists, so we have to do a profile. And basically, the blue line is going to show you the phosphorus stock. So this is how much phosphorus in terms, the red line is the phosphorus stock. This is grams per square meter. I'll give you the units in pounds per acre in just a second. What I want you to focus on is how much it varies. The right-hand graph is a summary. Across all these locations, phosphorus can vary quite a bit. So we can't simply generalize across even a small tributary of the Embera what the erosional load will entail in the phosphorus load sense. Here's some examples now in pounds per acre. This is one example of a small creek that we looked at. And so the top right-hand side is showing you the different layers that we profile, the P content. This is total, not test, and ppm. And then we looked at the sediments as well. And to our surprise, the sediments were fairly high. We know that sediments tend to have less P because the DRP is washed off already, but it can be appreciable. It's comparable to some of our soils. So that's the first finding. The second was that if you do the math, this 95-inch deep bank that you see on the top figure, if you do the math on how many pounds of P per acre are lost by erosion, we're talking almost 13,000 pounds. But we're not eroding an acre, we're eroding inches, right? So we're eroding inches over a length. So in this example below, if we get, say, a 6-inch erosional loss event, that's pretty big, right? We're losing 6 inches of the bank over just 3 feet length. So imagine a 6-inch rainstorm like what we just heard about. That will entail 3.2 pounds of P being lost. That's from 3 feet. We have thousands of miles of these streams. So 6 inches is a very big loss event, but what if we're chipping away ½ an inch every single year? This can add up appreciably. So in our state, our neighboring state of Iowa has recently come up with some estimates of how much can stream bank erosion contribute to total riverine export. So any guesses? And I know some of you know this number, so I'd ask you to zip it and let others guess. So any guesses as to what Iowa is conservatively estimating, because they didn't look at all of their streams. What do they figure is the total 18-year average stream bank contribution to the state's P losses as a percent? 25%, okay. Any higher takers on that number? Lower? 10? 70? Okay, I like it. So we got from 10 to 70. It's roughly a third, 31%. This is conservative. They think it's higher because they missed these small streams, which are net sources typically of phosphorus by stream bank erosion. Illinois, any guesses on this? I heard mumbling, but not a number. 40. 40, okay. I like the boldness. Thank you. Well, the question mark was right there. I'm sorry, I gave it away. So we have no idea, basically. We have no estimates. I flubbed that one. Okay, so our neighbor just found that maybe a third of their state riverine export is stream bank. And the way that we calculate non-point sources is by difference with total versus point sources. But that's not necessarily the same as equating the non-point remainder of the math as agricultural. So that means that if this were the case in Illinois, we have reason to think it's probably similar, right? That we're counting a large chunk of our non-point unfairly to agricultural sources. And I mean unfairly in terms of any BMPs that we invest in may not work the way we think. And second of all, we could also be targeting stream banks as a effective steering of resources to decrease on these non-agricultural, non-point sources. So within non-point, I think we should distinguish ag from non-ag. Stream banks are point and center, a really key non-ag, non-point source. Okay, so here's the math on the numbers. This is what we're hoping to do now for our state. You look at basically how much sediment is slowing off, the amount of bank that retreats, the length, you get a volume, the P content gives you the pounds of P. So Iowa's numbers look like this. This is a recent paper put out a few months ago, and they find that they're getting about 16.3 million tons of sediment, entailing this much phosphorus, but in pounds, that's 16.9 million pounds of P, which is pretty much what we're trying to decrease our statewide loads by in the final milestone target. So I'm not saying that we can stop all stream bank erosion, but it might be a really ripe, low-hanging fruit to begin to target for efforts on mitigation. Okay, and the final implication of this that I will end on is going to be that the stream bank then will entail a new kind of legacy P, which is legacy P in the stream bank. So this is not the soil legacy P definition. This is stream sediments already working their way down the channels. And as we heard, this is an issue because it can lead to annual variability in rivers and floodplains being sources to sinks. You get desorption, resorption of DRP. You have different forms of phosphorus in the sediment. Some are calcium phosphates, they won't dissolve. Some will even mineralize as organic phosphorus. So there's different degrees of slow release of these sediments. And this is important to quantify because it means that we might have quite a long time before the sediments stop leaking. Again, this is an erosion challenge, a soil conservation challenge, and a stream bank stabilization challenge, not a fertilizer over application challenge, but is no less important to quantify so that we can then try to manage it. So I think I'm going to end then on this slide, which is going to be, if you take away a theme in terms of the legacy phosphorus, it's that there are lags. There are also benefits and negatives to these lags. So in terms of the not so great implications, it means that there might be a long time before we see a BMP put in place to when it will register as a change in TP, the loads of phosphorus. Second is that we should probably quantify this because we're a little bit in the dark as to when is the sediment going to stop leaking phosphorus. And the third implication is that those subsoil P-supply power maps that we were just talking about, they might be rendered a little bit useless. I hate to say this, but if you have, from what Grandpa put down as swine manure in the 1930s, a lot of P banked up in that field, you've now just decoupled your field even from our forthcoming updated subsoil P-supply power map. And it's tough to gauge that with a soil test. So this is being very transparent with you. That's going to be a tough nut to crack. So I think I'm at time, so think we've got 1 minute for questions. Thank you for your time. I'll be around all day, happy to talk more about legacy phosphorus. Thank you.
I think focusing on phosphorus loads from the stream bank erosion is an important thing to consider because as we heard from the first presenter regarding weather data, the rainfall events are becoming more intense. And I actually did a fairly extensive term paper on, where does most of the stream bank erosion come from? Does it come from, normal flow periods or high flow periods? And a grand majority of the stream bank erosion occurs during high flow periods. And with more intense rainfalls, I think that this potential source of phosphorus could increase with time given more intense rainfall events. So it does make a lot of sense to focus there, in my opinion.
Just to be clear, you're saying to focus on stream bank erosion doesn't make sense. Oh, it does, excuse me, okay. I would agree with this. And I think, I think it's what you just said, I couldn't agree more, that the increasing intensity of rainfall events in the stream and in the floodplains are gonna be entailing potentially a lot of remobilization of the sediments, as we heard from the second speaker, and then also there's more slowing off of those banks, so yes.